All right, this is the fourth video on acids and bases. We see here that the lower the pKa, the stronger the acid. And now we have to compute the Kb value for each of these. Well, Kb for acetate is simply Kw divided by the Ka for acetic acid. And since we know what that value is, we can plug both of those in and get 5.6 times 10 to the minus 10th. And we can do the same thing for hypochlorite, because its Kb is going to be Kw divided by the Ka for hypochlorous acid, and we get 3.3 times 10 to the minus 7th. Now we need to describe the relationship between Ka of an acid and the Kb for its conjugate base. So this makes sense that if an acid has a large Ka, then its conjugate base is small. Ka and Kb are inversely proportional to each other because their product has to equal Kw. All right, section 9, acid-base properties of salt solution. This is an interesting situation here. Salts of these acids and bases can themselves be acidic or basic. When an anion reacts with water to generate H plus or OH minus, this is called hydrolysis. So we've got these 7 anions of these 7 strong acids that we memorized back in section 2. Do any of these act as strong bases in solution? The answer, of course, is no, they don't. Do they act as weak bases? No, they don't. Therefore, do they have any effect on the pH? No, they don't. And these 7 ions act as spectator ions. They're just hanging out, not participating in a reaction. Acetic acid, on the other hand, is a weak acid. So we can write an equation for the hydrolysis. So I have the acetate ion plus water reacts to form acetic acid plus OH minus, because the water is a stronger acid than the acetate ion is, so it donates a hydrogen ion. So based on the equation in part B, sodium acetate behaves as a base because it's going to produce OH minus. So a solution of this is going to have a pH that's higher than 7. All right, the salt of a weak acid produces a basic solution, and therefore we can say the salt of a weak base will produce an acidic solution. All right, so here I've got a couple of reactions of hydrogen phosphates with various values of Ka and Kb. In reaction 1, the hydrogen phosphate ion behaves as an acid because it makes H+, and in reaction 2, it behaves as a base because it behaves as a base because it's generating OH-. Will a solution of sodium hydrogen phosphate be acidic or basic? It's going to be basic. And the reason is that Kb for hydrogen phosphate 2- is larger than the Ka for hydrogen phosphate 2-. So it's going to more likely behave as a base than as an acid. And we need to write in part F an equation to show how ammonium behaves in water. And since ammonia is a weak base, ammonium is going to be a weak acid. And we write it like this. All right, the Kb of ammonia is equal to 1.8 times 10 to the minus 5th. We can calculate the Ka for the ammonium ion because that's going to be Kw divided by this Kb. And when we do, we get 5.6 times 10 to the minus 10th. How do the ions, and you see these cations there, affect the pH of an aqueous solution? Well, in the same way that the anions of strong acids don't affect the pH, the cations of strong bases also don't affect the pH because they don't form H+ or OH-. Now, according to this figure at the right, how can the Fe3+ ion behave as an acid? Well, the interaction between the ferric ion and the oxygen of the bound water molecules weakens an OH bond, and a hydrogen ion is lost. The charge changes from +3 to +2. I create H3O+, which makes my solution acidic. All right, here is a summary. I'm not going to read this to you. You can look at this yourself. This is going to be invaluable. There is a fourth possibility to consider. A salt may contain both an acidic cation and a basic anion, and in this case, the behavior of the salt depends on the relative strength of these two ions. Oops. If Ka for the acidic cation is greater than Kb, the salt should be acidic, and vice versa. Section 10, acid-base behavior and chemical structure. All right, the strength of the HX bond tends to decrease as an element increases in size. The higher the bond energy, the more difficult it is for that bond to be broken. So question C says, how does the data in the table above help to explain the difference in acid strength between HF and hydrochloric? Well, when HX reacts with water, it forms an acid. The weaker that this HX bond is, the more likely it is to break and form an acid, and vice versa. And this means that HF is a weaker acid than HCl, which clearly means that of these four, hydroiodic acid will be the strongest of these four halogen acids. Now, moving left to right across a period, electronegativity will increase, and moving top to bottom, it's going to decrease. Item E, which bond is more polar, HO or HF? And how does this difference explain acid strengths? Well, kind of a long explanation here. But since the electronegativity of fluorine is greater than the electronegativity of oxygen, the HF bond is more polar than the HO bond, so a molecule of HF is more likely to give up the H plus ions than a molecule of water. So HF is more acidic than water. The bonds are easier to break, therefore the acid is stronger. As I go down the group, the bonds are more polar, and therefore the acid is stronger as we move to the right from the left across a period. We can summarize this. We can say acid strength increases as we move to the right and as we move down. Now, which atom is more electronegative, chlorine or iodine? And how does this difference in electronegativity explain the difference in acid strength? Well, it's pretty obvious that chlorine's electronegativity is going to be higher than iodine, and as the electronegativity of this halogen increases, the electron density shifts towards it, the bond becomes polar or more polar. The protons are more readily transferred to water, leading it to increased acid strength, and we're going to see this in the Ka values. Now, we need to explain why chloric acid is a stronger acid than hypochlorous acid. All right, the strength of an acid increases as the additional electronegative atoms bond to the central halogen. So when I compare strengths of acids of hydrogen, chlorine, and oxygen in the sequence hypochlorous, chlorous, chloric, and perchloric, I can see that the strength gets stronger as I add oxygen atoms to the molecule. All right, item H, we need to talk about a carboxyl group and explain how this resonance helps explain the stability. Well, here is a carboxyl group. It's really just this thing attached to some organic molecule. This thing is the COOH, where the H, that's my acid H. All right, so the R group is just some organic molecule. Could be one of several different things. In formic acid, the R is simply a hydrogen atom. In benzoic acid, the R is a benzene ring. In both cases, I've just got a COOH attached to it, and that's our organic acid group, our carboxyl group. And we call these carboxyl groups which form acids carboxylic acid for obvious reasons. Now, the resonance improves the stability by spreading the negative charge over several atoms. I have these different resonance structures, and so these resonance structures allow these negative charges to be spread out, which helps in the stability of the atom. All right, that concludes our discussion about acids and bases. We'll have another group of videos about buffer solutions and solubility products. But that will come a little bit later.